Hello. Today I'm going to try to offer you a basic introduction to computers. And to do this, I'm going to take a little bit of an unorthodox approach. It's kind of going to be a problem-solving approach or a design approach. We are going to try to write a program that can solve for any permutation of a Rubik's Cube on a computer, okay? And if you're a complete beginner, which I'm going to assume you are, don't worry if you have no preliminary knowledge on Rubik's Cubes or computers. We're going to go really slow and we're going to build the necessary groundwork or knowledge base for you to keep up and fully understand. All right? So starting off, I want to begin with this book. This book is something I read a while ago called But How Do I Know? And it opens up with an old joke that goes, well, the salesman is trying to sell the first thermos to this guy named Joe. And so he tells Joe it keeps hot stuff hot and cold stuff cold. Joe is not the brightest and he's never seen a thermos before. So he answers, wow, but how do it know? Joe thinks maybe there's a heating component or maybe a refrigeration component inside the thermos, and whether you put hot stuff or cold stuff inside, it'll detect it and then maybe activate one of these components. But in reality, we know a thermos is a lot simpler than that, right? And the author opens up with this because he believes people kind of see computers as Joe sees his thermos. They do all these amazing things for us, and so we kind of assume there's a huge complicated process behind them, but in fact it's a lot simpler than that. Okay, so as we move along on the sections, you'll slowly kind of realize that truth. All right. This is what we're going to be working on. So given this, okay, so given this input, which is a scrambled cube, we want to somehow, we're going to touch upon this later, somehow give the scrambled cube to the computer. And then we want the computer to spit out a set of moves to solve the cube. Okay? We're going to focus on, obviously, this middle part, but we're also going to take a look at the problem, because the better you understand a problem, the better you can kind of gain an intuition on what the easiest path to a solution will be. We're going to take this in 3 sections, really. We're first going to build our knowledge base on a basic computer, and then I'm going to give you an introduction to the Rubik's Cube, and then finally we're going to put together everything that we've learned, and I will show you the final program that I wrote. And I hope by the end of it, you'll kind of gain an intuition on how computers might move things around to solve certain problems. Okay? To begin, computers obviously work with numbers, but they don't work in the same base that we humans do. So we really like the decimal system, whether it's time or any unit of measurement, really. We use the decimal system, and this is base 10. What that just means is, as you scale up in the digits place, it means a larger in 10 magnitude. So if we have the number, let's say 101, what that really means is 1 in the 100s place, right? Nothing in the tens place because there's a 0, and 1 here. So it would really be 100 plus 1. That is how our number system works. Same thing with the binary, except binary is base 2. This means as we scale up in these digits place, the value that it corresponds to increases by a multiple of 2. This is really, honestly, probably simpler because in base 10, whatever is in these digits places, it can be either, well, anything from 0 to, oh, it kind of looks like a 10, sorry. 0 to 9, right? But in binary, it can only be one of two things, either a 0 or a 1. As an exercise to try to really let this sink in, let's try to convert these 4 numbers from decimal to binary. And then by the end of it, it should make a lot more sense, okay? Starting with 2. How do we convert 2 to 4 places of binary? I think this should work. 0, 0, 1, 0. So that means we have 0 in the 0 eighths plus 0 fours plus how many 2's in the 2's place? Okay, so we have a 2. And then how many 1's? We have no 1's. So no 8's, no 4's, no 1's. We only have 1, 2. Nice. So this would be the 4-digit binary representation of the number 2. So do you kind of see what we're doing? It's really just finding a sum of these 4 numbers that can equal this number. Let's try 6 now. 6, 0, 1, 1, 0. Why? Because let's see. Is there anything in the 8th place? No. Is there anything in the 4 place? Yes, we have a 4. Is there anything in the 2 place? Yes, we have a 2. Anything in the 1 place? No. Cool. What does that equal? 6. Nice. Let's try 13 now. 13 would be this. Right? So we have an 8, 1 in the 8 place, 1 in the 4 place. Any 2's? No, we don't. Oh, no 2's. And we have a 1. Add all that up. Nice. We got a 13. 15, even without trying to find a sum, if we know this is 13, well, what do we need to add from 13 to 15? A 2. Great, so it should be pretty clear that it's the exact same thing, except the 2 place in 13 is now a 1. So same thing as the one above, but this time we add a 2. We have a 2's place, right? 15. All good? Cool, let's move on. All right, this section is going to be a little trickier than the previous ones. I'm going to kind of introduce the basic idea of computers and how they move things around, okay? Let us consider, you ever see those mailboxes in apartments? It's like a big stack of mailboxes, and they're all numbered for the certain however many room numbers there are. Here, let us consider an apartment of 12 rooms. And so when you walk through the front door, you see this as a mailbox. 12 different mailboxes, all numbered from 1 to 12. Now, what we're kind of referencing, the technical term for this would be RAM. And what this really is the memory of the computer. I chose the analogy of mailboxes because there are two properties of mailboxes that is exactly the same as RAM. Two properties that we care about. The first one being the address. So what room number? And the second being the content of the mailbox, whatever the mailbox holds. Okay? And then we also have these three buckets. Now, these buckets, the analogy, I guess it's the technical term for these will be registers. I really don't want you guys to get hung up on the technical terms of computers. The goal should be just trying to create an intuition in your brain on how a computer might do things. Okay, so we honestly don't need to worry about these terms. Anyway, so these buckets, what they're used for is to view the content inside these mailboxes, or to move them around. We first have to take the contents of any certain mailbox and then put them in the buckets. Okay? That might not make sense right away, but we'll work through an example problem and then hopefully it'll make more sense. With this system, let's see if we can do something simple. Okay. Let's try to add two numbers. Let's try to add two numbers with this system. And to do this, we are going to use these instruction sets. Okay? We might not need to use all of them. We have 5, so we have load A, add, store A, out, and halt. Maybe we'll need to use all 5. Maybe we won't. Yeah. Okay. So let's choose to maybe add 3 and 4. Okay? First thing we have to do is we have to show the computer those two numbers. And we have to store it somewhere. Let's choose mailbox 11. Let's store 3. And 4, let's put that in mailbox 12. All right? Let's see. Okay. So how a computer will search through their memory is they'll go in numerical order. So they'll look at mailbox 1, and then they'll look at mailbox 2, and then 3, and then 4, and then 5. And it'll go, and it'll keep going. Okay? Let's see. What is the first thing? If we put load LDA in mailbox 1, when the computer sees this, it'll recognize this action, and then it'll follow, let's see, load A with mailbox whose address is in the next box. Okay, so if we put 11 in the next box, let's see what would happen. So we will load A with mailbox of address 11. What is in 11? 3. Cool. Let's move 3 into bucket A. Great. Now let's see. What else should we use? So we've used this one. Maybe let's try this one. This one is called add. What does it do? Load B with mailbox whose address is in the next box. Okay, so the next action we want to take is add. And what do we want to move to bucket B? I think we want to move 4. What is in 4? Okay, what holds 4? 12. So add 12. It'll look in what is in 12, move it to, load B with whatever is in 12. So let's put 4. and B now. It'll add A and B, so 3 and 4 add is 7, and then it'll load A with the result. So now A no longer is 3. A is the result of the addition, which is 7. Cool. Now, what should we do? Now that we have the result, I think it's time to send it to our output, right? So let's write out. What this will do is it'll copy whatever's in the register and move it to the output. Nice, we've done it. We've put 7 in our output bucket. Now the only thing that's left to do is we'll use, so we've done this, and now we'll do this one. We'll halt it. That just means stop the program, because if we don't have this, the computer will keep looking to the next box and the next box and the next box. But we've already done what we wanted. We are printing the number 7. Okay? I know that was a whole lot, but that's only because it's new, okay? Great. Oh, I should also add, these actions that we've done, you can really have an unlimited amount of these instructions. It's just whatever you want to use. You know, these can be designed for. You can really use you can make the computer do anything as long as you're following this design structure of, you know, moving certain mailbox contents to another mailbox, and then if you want something, you know, you'll look in another mailbox and then you'll copy that. This is the general structure that I kind of want you to gain an intuition on. All right? Nice. So now that we've covered the basic structure of how a computer will move around and manipulate data to do something, let's finally move on to the Rubik's Cube, okay? So remember the apartment mailboxes from the last section? Now I want you to imagine another set of 8 mailboxes, okay? And they're all numbered 1 from 8. And in each of these mailboxes, we have a card. There are 8 cards numbered 1 to 8, of course, but they're out of order. We want to put every single card in their right mailbox. So let's, for example, the second mailbox, we have the number 8, the card with the number 8. We want to put that in the 8th mailbox, and so on. Okay? How do we do this? Well, this is relevant to how we're going to solve our Rubik's Cube. There's a lot of ways to solve a cube, but funny enough, the way you would teach a beginner is, I don't believe, the easiest way for a computer to solve it, or at least the way that I designed it. So the way a beginner would be taught is, well, they would make a move, right? And then they would reassess the cube, because when you make a move, you're moving a lot of these stickers around. And then based on that new reevaluation, they're going to make another move. And they're going to repeat that process. They're going to make a move, reassess what is the next move I can make, and then they'll make that move. But that's a whole lot of, piece tracking. And the method that we're going to implement is called classic Pachman. And this method is actually how people solve a cube blindfolded. Why is this important? Well, or the better question is, why do I believe this is easier? Because, well, when you're solving it blindfolded, you're given the cube, right? You take a look at the unsolved cube. You're blindfolded, so you can't track pieces anymore, or at least it's extremely, extremely difficult to do that. So you have to find a way to take a look at the unsolved cube and immediately know the entire sequence of moves you have to make to completion. That seems really difficult, but once I show you the sorting algorithm that method, classic Pacman, is based on, you'll see it's really not as complicated as you would imagine, okay? Honestly, it's probably the same level of complexity as the method a beginner would use to solve the cube. Okay, so going back to the mailboxes, it would be difficult for me to explain, so I'll show you and you'll see how simple it really is. We'll call one of these mailboxes our buffer mailbox, and this can be any of these mailboxes. For our purposes, we'll just arbitrarily pick number 1, all right? And we will only look at the contents of what is in mailbox 1. We look inside our mailbox, we see the number 6 card. So without even looking at what is in 6, we don't care. We will just put 6, put that card there, and swap it. So we will swap 1 and 6. And now we'll look in mailbox 1, and we'll do the exact same thing. Now we look, there's a 4. Let's swap mailbox 1 and 4. Now we look at what is in 1. 2. Let's swap mailbox 1 and 2. Do that again. What is in 1? 8. Cool. Let's swap mailbox 1 and 8. Oh, sorry. What's in 1 now? 3. So let's swap 1 and 3. Now we have a 7. Let's swap 1 and 7. What's in 1 now? Our buffer mailbox? 1. Interesting. Okay, so 1 has returned, and let's look at the rest of these mailboxes. 1 is in 1, 2 is in 2, 3 is in 3. Okay, it appears solved. All right, see, really not that complicated. All we're doing is we're looking in the contents of our buffer mailbox, and then we'll just swap with another mailbox. That's it. We'll just keep swapping, keep swapping, keep swapping until we see 1 back in our 1 mailbox. Got it? Now let's try to see how we'll implement this sorting algorithm to a cube. Okay? Cool. All right. If we take a closer look at a Rubik's Cube, you'll see there are, well, all cubes have 6 sides, right? We have a front side, top, back, right, left, and bottom. And each of these sides has 9 pieces. And these 9 pieces we can categorize into 3 different types of pieces. Okay, we have the first piece, the first type being the centerpiece. And this centerpiece we don't really care about because it's always solved. Why do we know this? Well, because no matter how you turn the cube, no matter which moves you make, the centerpiece never actually moves. So the centerpiece is always right. We don't have to solve for it. What we do have to solve are the next 2 types. The first one being edge stickers. And there are 4 edge ones. There's this one, 1, 2, 3, 4. 4 edges. And then the remaining 4 stickers are 4 corner stickers. 1, 2, 3, 4. 4 corners. All right, so 4 edges and 4 corners. So there are 8 stickers on any individual face that we need to put in the right place. Since we have 6 sides, that would be what? 6 times 8, 48, I believe. 48 stickers that we have to orient. I don't know what. Okay. Yeah. So how do we do this? Well, for each of these stickers, let us assign a letter to them. Okay? So if we take a cube and pretend it's hollow, it's like a box. And then we cut it open and we spread out each face. This is the kind of layout that you would end up with. Okay? So the way I chose the orientation, I have red as our front. So I put red here and a little F. So this is our front face. Blue I chose as our up face. White left. Yeah, this is our right face, back face, and our down face. All right? Excuse me. And each of these, we give it a lettering scheme. So for corners, we start with this one, our upper back left one here is our first one that we letter A. And we will go clockwise on each face to letter them. So we have A here, and then B, C, D. And we'll move on. E, F, G, H. We'll go upper left, again, I, J, K, L. And we keep going clockwise on the faces. That's how we're going to letter them, okay? And the corner letters, I've obviously put an underline on them. So the edges are the exact same way, okay? Except we're going to start with the rightmost piece, or sticker on each face. So this one is the rightmost. That's a pen. Is the rightmost. So we call this A, and we'll keep going clockwise. So A, B, C, D. Rightmost, E, F, G, H. Rightmost, I, J, K, L. You can really letter them however you want. It doesn't really matter as long as we're representing any given sticker with a letter. This is just how I chose to do it, okay? And now we're going to repeat the same process with a scrambled cube, such as this one. So we take the cube, pretend it's hollow, and if we open it up, if we spread it out, and we use the same lettering scheme, okay, this is what we would get. And obviously, these pieces are all over the place. This is what the unsolved would look like, okay? So this top one up here is our correct location for the stickers. This is if we use the same lettering scheme, except, well, we scramble the cube, so we're moving the letters or stickers around, okay? If we take a look at what is in location A here, let's say this edge location A, we look, well, what is there? Okay, now sticker W is in the place of A. Okay. If we look at the edge mapping, this is kind of a summary of the relationship between these two, okay? So we look at what is in A's place. Well, W is in A's place. Same thing with the corner. We can try the first one, A. This is the correct location for A, the correct address for A, I should say. Let's see, what is in Okay, B seems to be in the A location. All right, now this upper map here, this is exactly the same as what we did here with the mailboxes. You know, we have the correct location for the cards. This is the correct location for card number one, correct location for card number 2, correct location for card number 3, and so on. Okay? This is the exact same thing. Up here, what we have is the correct location. These are the mailbox numbers, the mailbox addresses. And this is what we have when we scramble the cubes. Okay? How do we solve it? Well, we solve it the exact same way. There's an infinite amount of permutations for Rubik's cubes and an infinite amount of moves, different moves you can make, but we only need to care about these moves, okay? I don't really want you guys to worry about the numbers here or even the sequence. These sequences are just a certain sequence of moves you make with a cube. This is just the notation that people who cube use. I don't even need you to worry about that right now. Just know that for every letter, let's say B, corner of B, there is a move that we can, if we do this, we will swap the A and B, this one and this one. We will swap these two corner stickers. We'll swap them around. Do you kind of see how, or do you kind of see where this is going? Well, the way I lettered it, I have A as our buffer location or address, however you want to call it, okay? And we have a set of moves to swap whatever is in A with any other sticker. So whatever is in corner piece A, we have a sequence of moves that we can do that will swap whatever's in corner A with any other corner sticker of the cube. Okay? So this is exactly what we did in our mail sort. We just swap whatever is in our buffer, which we chose as 1, on the cube is going to be A, and we swap it with another sticker. And we swap and we swap and we keep swapping. Okay? So if we start at the buffer, just like we started at mailbox 1 for the corner, we look at what is in our buffer mailbox. A. Well, B is in A. B is in A. So what is the first sequence of moves we have to make? It's going to be this. This is the first sequence of moves we have to make on our road to solving it. All right? Now, how we're going to go about the whole process is we're going to swap all the corners with our buffer until our A sticker comes back to our A, the correct A position. Just like the mail sort, we stopped when the one card came back to the correct one mailbox, which was our buffer. Let's try to find where our A corner is. So where is our A corner? Here it is. So when this goes back to this position, when that happens, we will know all the corners are solved, okay? First, we solve all the corners, and then we solve all the edges. Really, you could do it the other way. You could solve for the edges first, and then the corners, but you have to make sure that you solve all of one type, either edges or corners first, before moving on to swapping the others, solving the others. One last thing I have to mention about this method is, let's say you do corners first. If you have an even number of swaps, you make an even number of corner swaps, then you don't need to do this sequence. Okay? And if you do have an odd number of swaps, then you do have to do this. This is called parity. Very simply put, this is just something that you have to do after doing your corner swaps before moving on to your edge swaps. You don't really need to worry about why. Just take it as it is and just know that this is something that you have to do, okay? So we swap all the corners until A is back into the A position. Once we've done that, we count how many swaps we did. If that number of swaps is odd, then we have to execute this sequence of moves before going on to solving the edges. If the number of swaps that we made in solving the corners is even, then we can move straight to swapping the edges. All right? That makes sense? Awesome. Now let's move on to our very last section where I show you the completed code, which is this. Okay? This might look scary at first. There's a whole lot going on, a lot of numbers, but I assure you, this is nothing that we haven't done yet. To begin, I should say, you know what? We'll use blue. These gray numbers that you see here, these gray numbers this is still the exact same mailbox system, okay? These gray numbers are just the mailbox address, the numbering of the mailboxes. So this would be mailbox 1, 2, this is mailbox 1, this is mailbox 2, and the white, of course, is whatever is in those mailboxes. And you probably recognize most of these commands. You know, we have load A, and 48, and so on. So do you remember from our previous sections, actually the second section, this one, where we kind of spoke about how we're going to touch on how we present the scrambled cube to the computer. All right, so computers don't have eyes like we do, so we have to show the cube to the computer somehow. Well, this is how I chose to do it. I chose, starting from mailbox 48, I chose to represent this as A. 49, mailbox 49 would be B. Mailbox 50 would be C. Mailbox 51, D, and so on. We keep moving down in alphabetical order. In this, we represent the corners. If we take a look at the first mailbox, mailbox A, okay, so sticker A, what is in mailbox A? 49. What does 49 represent? B, of course. Okay, so 49 is in mailbox 48. This means is actually B is in mailbox A. Sound familiar? Well, let's go back to our cube sort. B is in A. Right, so what we did here with the corner mapping and the edge mapping is exactly what we're doing here. We're just representing each letter as a number. So we're just picking a mailbox for any certain letter, okay? We did the exact same thing with mailboxes for edges, except we started A, which is our buffer, is 78. B, oh, I should probably underline these so we can differentiate. C, and so on. All right. Now let's walk through what our program is doing exactly. And we're going to walk through step by step, okay? First thing that we do, load A with 48, okay? Load A with 48. What is in 48? 49 is in 48. Cool, so we will load A with 49. And then we will subtract 73. So that means we'll put whatever's in 73, which is 48, in bucket B, subtract it from A, and put the result in A. 49 minus 48 is 1. So we will put the result of 1 in bucket A. Great. And then the next command we have JZ22. This is something new that I have to explain. This just means whenever you see a J, it stands for jump. JZ specifically means jump if A equals 0. Well, you know how computers read one to another in order. You know, they'll look at each mailbox, read it, and then move on to another, and then move on to another. Well, jump means if we jump 22, it'll, after looking at mailbox 6, it'll just jump, it'll ignore all of these and then jump straight to 22. But this is something called a conditional jump. So it'll only jump to 22 if A, whatever is in bucket A, is equal to 0. Okay? Later on, we have this, which is a jump, an absolute jump, JMP, which just means no matter what, we will jump. Once we get here, we will jump back to mailbox 1, and we'll start reading again. Okay? All right, so jump if A equals 0. Right now, we look at A. A is 1, so we don't jump. We just keep moving on to 7. All right? So let's freeze here and think about what we did in the first 6 mailboxes, okay? We are loading something, loading whatever's here, into our mailbox, and then we're subtracting 48. And we're only moving on to mailbox 22 if it equals 0. Why do we do this? Well, what is the one way in which A can equal 0 if we're always subtracting 48? Right. If A is initially 48, because 48 minus 48 will get 0, and we'll put the result in our bucket A, and then we'll jump. And what does 48 represent? Well, 48 represents A. So what are we effectively doing in these 6 mailboxes? We are checking if the A sticker is back in the correct A location. This is exactly the same thing we did with our mail sort or our cube sort that we talked about. We only move on past the corner swapping once A is back in the A position, because then we'll know all the corners are solved. Same way in our mail sort, we stop once 1 comes back to our buffer mailbox of 1. Then we'll know the rest of these are solved. Okay? That is all that we're doing here. Makes sense? So let's move on now to the next section. Seven to 9, what are we doing? So we're loading 48 once again. So A would be 49, because 49 is a contest of 48. 49. And then we are printing that 40, whatever is in A. So the computer will show us the number 49, right, from this output. And do you remember from this previous section where I said don't worry about the numbers here? Well, now we're going to worry about it, okay? So each of these sequences of moves that we use to swap two pieces, well, we assign a number to them. So the first one was a B, right? B was an A, and we number this as 49. So when the computer shows us the number 49, we know that this is the first sequence of moves that we have to do. And so if it shows us some other number, let's say 62, we'll know that this is the sequence of moves that we must do. We also know that effectively what we're doing is we're swapping the buffer sticker with the O sticker. Make sense? That is why we show what is in A. Moving on to the next part. We're almost there. So store A into. This is a new thing. This just means store in whatever mailbox is presented here. Store A, sorry. So this is telling us to store whatever is in A in mailbox 2. Right now we have 49, and let's store that in mailbox 2. Mailbox 2 currently holds 48, so we are going to overwrite that, and now 49, the contents of A, is there. Next, we store A in 8. So we'll do the same thing. We'll store this 49 in mailbox 8. Mailbox 8 also had 48. Now we rewrite that to 49. Any idea why we do that? Well, because this is going to be a loop. Once we're done, we're going to jump back to 1, right? Once we reach this point, we're going to jump back to this mailbox. But now we are going to repeat this loop, not with 48, which is A, but now with B, because now we look at what is in the B mailbox, and then we'll swap whatever is in B with that respective box, and we'll keep swapping, all right? So what we're doing here is we are just self-modifying our own code so that it follows the chain of swapping. This is exactly the same as what we did here with our mail sort, okay? Exactly the same. We just keep following the chain. We look what is in A, cool, we'll make that swap, and then we'll make another swap. We'll look at what is in A, we'll make another swap. What is in mailbox 1, we make that swap. And the final section here. Sorry. Let's take a look. Load A with 75. What's in 75 right now? 0. Cool. Let us load bucket A with 0. And then add 76. What is in 76? 1. Cool. So we put 1 in bucket B, add the 2, and put the result in A. A now holds 1. And then we store whatever is in bucket A in 75. So 75 used to have 0. Now we overwrite it with the contents of 1. 75 has 1. Cool. And then we jump back. Let's think for a moment. Why did I write this portion? Well, 75, mailbox 75 is effectively just serving as a counter. It's just a counter. So every time we go through this loop, we will continuously add 76 to 75. 76 is just 1. So every time we go through the loop, we are incrementing 75 mailbox 75 by 1. Why is this important? Well, every time we go through this loop, we are swapping something, right? So we're just counting the number of swaps. Going back to our cube sort, the last part that I mentioned in this section, the parity sequence. Once we're done the corner swapping, we need to know if there is an even or odd number of swaps. To do that, obviously, we have to count the number of swaps that we make. That is exactly what we're doing here. Okay? And then we'll jump back to 1, and we'll repeat with B, and then the next letter, and then the next letter, we'll keep swapping them with our buffer. Eventually, A will come back to here, and we'll get 48, 48, and then we'll subtract 48 from 48, we'll get 0, and then A is back in its position, we go to parity. And I'll give you a bit of a spoiler. This counter, once A is back in its position, we will have gone through the loop 7 times. Okay, so 7 corner swaps. Onto the parity check. Here, what we're doing, oops, this is the pen. This jump carry just means jump if even. Okay, so jump where? We're jumping to 31. We're jumping to 31. That means we don't do this part over here, which is load immediate 200 and out. What that just does is it'll take the number 200 and just print it. The computer will show us 200. Why 200? Well, we have already assigned the parity solution to the number 200. So now we know if the computer shows us 200, it means do this move, this sequence of moves. All right. Now an important question arises. Well, okay, so how does, even though we've tallied up and we know the number of swaps we made, how does a computer identify if a number is even or odd? Okay, well, to answer that, let's go back to the language that they use. Okay, so they use binary. These 4 numbers that we've converted, this one is even. 6, also even. 13, odd. 15 is odd. If we look at their binary translation, what is one thing that the odd numbers have that the even numbers do not? Well, they have a 1 here. They have a 1 in the ones place, and the evens have a 0 in the ones place. This should kind of make intuitive sense because, well, decimal is the same thing. If we have the number 10,001 or the number 101, we kind of don't care about all these numbers. As long as we have 1 in the ones place, we know that this is odd, right? The same way if we have just 10,000 or 100, if we have 0 in the ones place, we know this is even, no matter how many numbers come before or after it. All right? Same thing with binary. As long as this is a 1, we know this is odd. As long as this first number is 0, we know this is even. Cool. So our computer is just going to check this last bit, and it will jump to here if it is even, jump to, and then it'll ignore it if it's odd, and it'll do this. It'll show us 200. Make sense? So if it's odd, it'll show us this 200, and if it's even, it'll ignore it, and we'll go straight to the edges loop. Now, the edges loop is the exact same thing as our corners loop, except we don't have to do this last part of tallying up and counting our swaps, because we only did that to check the parity. And our JZ, our jump, if A 0, of course we're subtracting 74 now, which is this one, which is 78. 78 is our A for the mailbox of for the buffer A for the edges, right? And so if the edge, A edge, goes back to the correct A location, we know all the edges are solved, and then we will jump where? To 46. 46 is here, and we will halt. So, done. Our program is done. All right, to test our program as well as the computer, I'm now going to blindly follow whatever sequence of moves the computer tells us to make. This over here is the output section, and I apologize for the camera quality. It's a little difficult to see, but right now it's giving us all zeros. I have my cheat sheet here with all the sequence of moves we can make along with their corresponding number. This is the scrambled cube that I've given the computer. So let's give it a try and see what happens. $49 is the first one. And 71. $56. $57. $68. $69. $62. $200. Okay, we're going to pause it for a sec because 200 represents parity, and that sequence of moves I'm not too familiar with, so it's going to take me a little more time. But let's execute that right now. Cool. Let's continue. $100. 91, 96, 99, 84, 79, 88, 86, 81. Which one is 81? Oh, okay. Since our computer stopped, that means 81 is the last sequence of moves we have to make to completion. So let's do that right now. Nice. It works. Okay, before we close off, I just want to give you my final thoughts. Starting with, so this is the actual code that we put into memory. And this, the columns on the left that you see here, 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 these are the mailbox addresses. And this, again, looks kind of scary, but this is nothing that we haven't covered yet, all right? To show this, let's take the second row as an example. 0, 0, 0, 0, 0, 0, 1, 0. We translate that. That is just 2 from binary to decimal. And then here, 0, 0, 1, 1, followed by zeros. This is 48. We go back to this code. That's a little more familiar. Well, our second mailbox has 48. So this is exactly what is being shown here. It's just we translate everything to binary. Makes sense? Cool. Now, I think it's worth noting practical limitations of our computer, or sorry, the program that we wrote. And there are two things that it doesn't consider. And the first one is it doesn't consider if there's a chain break, and the second being if there are flipped edges or twisted corners. Now, I don't expect you to know what those mean, but I'll link a video in the description, and it's a video that I used to learn how to solve a cube blindfolded. It's the classic Pachman method that we implemented in this video. And those are just two really small exceptions that are very easy to learn. And the guy who makes the video is pretty awesome. He goes way more into depth than I do. And yeah, okay, so you should check that out. And as for theoretical, or yeah, one more thing. So the solution that we implemented, even this blind solving method, I'm not sure that this is the best way to go about this problem here. I've thought about this problem for a while, and this is just what I chose to do. You know, this is kind of the first thing that jumped out at me as the simplest. But as you saw in our demo, that was a whole lot of moves. I think in total it was 179 moves. And a perfect solution for any Rubik's Cube is 20 or less moves. So we're not even close, you know? And people who are really good at solving them, they typically use solutions that are 50 to 60, somewhere in that ballpark, that amount of moves. So we aren't even close to them, you know? So yeah, there's probably a better way to go about this. This is just the way that I chose to do it. And as for theoretical limitations, well, the biggest limitation would probably be just the number of mailboxes that we have, how much memory, right? If we go back to our code here, our program only uses 101 mailboxes. 101. And if you have, okay, sorry, I should say one of these digits in binary, we call this a bit. And once you have 8 of these bits together, like in our program, we call this a byte. You might have heard this term, gigabyte, before. You know, nowadays with modern computers, let's say if you're buying a laptop, the specs that you'll see is maybe 8 gigabytes or maybe 16 gigabytes. Well, gigabytes means a billion bytes, right? So here you have these computers, 8 billion. 8 billion of these mailboxes. We did something pretty cool using only 101. So you can imagine if you had 8 billion of these, what you could do. All right? So we opened up this lesson, lecture, or whatever you want to call it, with the opening of this book here. And the author closes the book with the conclusion of their conversation, where the salesman responds to Joe saying, well, it doesn't know anything.